Hi, I'm Brad McKay, and this presentation will review a few of the findings from a meta-analysis my colleagues and I recently completed. I don't need to explain to this audience the importance of the guidance hypothesis in the history of motor learning research. Briefly, the guidance hypothesis predicts that performance during acquisition is enhanced by providing feedback after every trial relative to a reduced frequency. However, when feedback is withdrawn and learning is measured with a delayed retention or transfer test, the guidance hypothesis predicts a reversal, such that learners who were provided a reduced frequency of feedback during acquisition are expected to perform more effectively during retention. One purpose of our meta-analysis was to evaluate whether the performance and learning hypotheses put forth by the guidance view are supported by the available data. Beyond hypothesis testing, another purpose of our study was to estimate the average effectiveness of providing a reduced frequency of feedback at both acquisition and retention. It's important to investigate the magnitude of potential effects to assess the practical importance of these results. To these ends, my colleagues and I conducted an extensive literature search for experiments that manipulated feedback frequency and included either immediate or delayed retention tests. We focused our search on randomized experiments that sampled from healthy populations and included objective measures of motor performance. We retrieved 60 articles in total that met our inclusion criteria. Our primary analysis pertained to performance on measures that matched the feedback being provided. For example, if in an experiment, participants were told their root mean square error as feedback, then RMSE was the measure we were interested in. If we were missing data required for our primary analyses after contacting the authors, we proceeded to digitize the figures that were included in the articles if possible. Before discussing our results, I'd like to highlight that each step in this process, from article screening to data extraction and plot digitization, was conducted in duplicate by 2 members of our team, each working independently. Our full search, extraction, and analysis plan was pre-registered, and our data will be made publicly available when we post the preprint of our results. Now for the results pertaining to the guidance hypothesis. This forest plot illustrates Hedges G estimates during acquisition. Hedges G scales the mean difference between the 100% and reduced frequency groups by their pooled standard deviation, such that an effect size of 1 suggests a mean benefit 1 standard deviation in favor of a reduced frequency of feedback. Each square on this forest plot represents the point estimate for a given experiment, and the error bars represent 95% confidence intervals. The dotted vertical line reflects no difference between conditions, and anything to the right of the line is a result in favor of a reduced frequency, while anything to the left is in favor of 100% feedback frequency. Just above the x-axis, the black polygon represents the point estimate and 95% confidence interval from a random effects meta-analysis of these data. As you can see, the results indicate no significant difference between 100% and reduced frequency groups at acquisition. Extending beyond the black polygon are error bars that represent the 95% prediction interval for these data. If we were to sample a random experiment from the same population of experiments the included studies were sampled from, we would expect a result inside this interval 95% of the time. As you can see, the prediction interval is enormous, ranging from huge advantages to huge disadvantages with a reduced feedback frequency. The data at retention are presented in this forest plot, and as you can see, they're quite similar. First, note that the black polygon above the x-axis suggests that there is no significant benefit, on average, for reduced frequencies of feedback at delayed retention. Second, and more importantly, note that the 95% prediction interval is again too wide to be useful. These results do not support the guidance hypothesis. Feedback frequency did not have a significant effect at acquisition or delayed retention, nor did the effect change from one time point to the next. Perhaps more importantly, our estimates of the average effect of feedback frequency were highly uncertain. The extant literature simply does not provide support for strong predictions about feedback frequency. Beyond failing to support the guidance hypothesis, these data demonstrate that we just don't know what the effective feedback frequency is. But what if the experiments have reported significant results one way or the other? We fit a Z curve to the delayed retention data to evaluate the effect that selection based on statistical significance had on this sample of experiments. The results suggested that direct replications of the significant results in this meta-analysis are likely to fail 80% of the time. The median sample per group in our meta-analysis was 13. This simply is not enough. If the average effective feedback frequency is 20% of a standard deviation, then to achieve 80% power, we would need 394 participants per group for an independent two-tailed t-test. Yes, we can improve our efficiency by using sequential designs, pre-registered predictive covariates, and one-tailed test of established hypotheses. But all of these efforts will still leave us requiring orders of magnitude more participants per group than 13. Naturally, there was a lot that went undiscussed in this 6-minute presentation. Please pop into the Q&A. I would love to chat more about this project.